Hi there, and welcome to another video for the course of algorithm design. This is one video in a series in which I'm trying to solve the same dynamic programming problem in several different ways. In this version of the video, we're going to be working backwards in 2D, whatever that means. But before I tell you all about what that means, please make sure that you familiarize yourself with this problem if you haven't done so yet. And that means pausing the video, really trying to solve the question yourself first, and only once you've done that, take a look at how I solve the problem. After all, watching me do it doesn't mean you are able to do it yourself. Trying to do it yourself, maybe failing to do it yourself, then watching me do it, that will help you to do better next time. So please try it yourself first, pause the video, read the question, really try it before you continue watching. With that, let's take a look. So, what are we tasked to do? We are tasked with writing an n-line poem about m special events. And each line should be about an event, and each event should have at least one and no more than k lines about it. And anytime we assign a certain event to a certain line, we get a certain emotional value for it. We want to maximize the total emotional value we can get. So what do we do? Well, one way to reason about it is as follows. We're talking about, at the start, we have n lines, let's say 100 lines. And we have 50 events. Now, I would like to make the problem smaller. That's how I like to think about this. So, how do I make the problem smaller? Well, what I could do is I could try to figure out how many lines do I want to spend on event number 50. Because as soon as I know, then I've made the problem smaller. I will have less lines, and now only 49 events left. So that will be the question for me to try and answer. And how many lines can I spend on event 50? Well, at least one, and no more than k. So let's try and come up with a mathematical formula, we'll call it opt, that encapsulates exactly this behavior. What do I want to do? Well, I want to explore k different options. I want to explore k different options. So, and this is a maximization problem. And I want to explore k options. So 1 between capital K. Now I need a first variable here. I would normally call it small k, but because the difference between my small k and big K isn't always clear, I'm going to call it alpha instead. And alpha represents the number of lines I'm going to spend on a certain event. Hang on which event? Well, I started this by saying, imagine we have the 100 lines in the 50 events. So apparently those are two parts of data that I need in order to reason about what to do. So I probably want an I and a J to indicate the number of lines left and the number of events left. And now, what happens when I have 100 lines and 50 events? I want to see how many lines between 1 and k do I want to spend about on this last event, on event number 50, event number j, I suppose. Well, I have every choice between 1 and k. All of them are an option. But what happens when I pick a certain number? Well, when I pick a certain number, I'm going to spend that many lines on this event. So I will have I minus alpha lines remaining. And those are all the lines I'm going to spend on this event. So I will now have one event less after this, because I've used this event fully. But in spending these alpha lines on this event, I also get a reward. And what is the reward I get? Well, I basically get all of these EIJ values. And which ones do I then get exactly? I was hoping to put that slightly lower. There we go. I get them from, and I need another iteration variable here. Let's call it t. Well, I want to add the reward for all of the lines that are now about event j. And which lines are they? Well, they are all the lines starting from I minus alpha plus 1 up to I. As an example, imagine that we have 100 lines and we choose to spend 5 lines talking about this event. Then which rewards do I get? Well, I get them for 100, 99, 98, 97, and 96. In other words, for 100 minus 5 plus 1 up to 100. From 96, 7, 8, 9 to 100. It's always a bit tricky to come up with these indices. For me, it helps a lot when I just come up with an example and try them. All right. So this is going to be the main bulk of my function. For each event, I try to figure out how many lines should I spend on it. Now, this is nice, but this is going to recurse infinitely unless I come up with some good base cases. So what are they? Well, when I have no lines left, and I also have no events left, I would like to return 0. There's nothing more I can do. But if I have no lines left, and I do have events left, then we have a problem. If this is the case, where I still have lines left, no more lines left, but I do still have events left, that is a situation we would like to avoid at all costs. Because this means the poem is not going to be valid. It's not going to be an n-line poem about m events. We're going to need more than n lines over all m events. And if it is a situation I want to avoid in a maximization problem, I want to make sure that I give here an answer that will never be picked. Well, in a maximization problem, what do we want to avoid at all costs? Minus infinity. Any other option will be at least as good, but hopefully better than this minus infinity. So this is what we do when we have no lines left, but we do have events left. And of course, it's also what we do when we still have lines left, but we have no events left. Because each line should describe an event. So if we have lines left but no events, we also have a problem. And if you look carefully at what we do here, there is one more situation we should be careful. Imagine that I'm allowed to write 1,000 lines about every event. Capital K is 1,000. But my poem is still only going to be 100 lines long. Then this function is going to call 100 minus 1,000. So it's going to call this function with minus 900 and one less event. So I need to make sure I also have a base case that covers what happens when I becomes negative. And well, when I becomes negative, this is a situation we again want to avoid because we have spent too many lines talking about a poem, about an event. So what we can do is we can add here as a base case, this should be an or. Sorry if you were screaming at your screen that was wrong. Or I is negative. If I is negative, that's a situation we want to avoid at all costs. There are other ways to fix this problem. An alternative would be, rather than adding this to our base case, we could also say here, well, we simply never allow alpha to become bigger than I. In other words, we pick alpha between 1 and the minimum of k and I. Is also fine. This way we can never exceed the number of lines either. So whichever one you find most easiest to understand is a perfect way to encapsulate this. course, we still need to talk about what do we call this function with. It's not like I recorded the video for this problem earlier where I totally forgot to do that. So let's talk about it here. Well, at the start, we have n lines left and we have m events left. So we call those opt nm. And there we go. This is a way to solve this problem, reasoning backwards. We start with the biggest version of the problem, and we make the numbers smaller and smaller until they become 0. We start, if you will, at the end. We first figure out which lines should be about the last event, and then we reason backwards. And it's in 2D because we have 2 parameters here, which means that if we were to implement this, these would be 2 dimensions in a recursive or in a memoization table. And there we go. This is one way to solve this problem. Now, while we're talking about the implementation, keep in mind that the time complexity of this looks like it might be pretty bad, because there's a maximization over many things, which would require a for loop. And then there's also the summation, which would require yet another for loop. At least that's what it looks like. But that's not really true. We can combine this in a single for loop by cleverly computing this either in advance, using something called prefix sums. But even if we don't compute it in advance, we don't have to, we can still increase this sum as we continue to the next value each time. Basically, when alpha equals 1, it's just one value, eij. Right? Because when alpha equals 1, it's I minus 1 plus 1, so that's just I. So it's from I to I, okay, so that's just eij. And then when alpha equals 2, we need to add I minus 1 j to it. And then when alpha equals 3, we need to add the next one to it, and so on and so forth. So we can actually compute this in constant time, provided that we have the previous iteration's value stored. So we can do all of this in a single for loop when we implement this iteratively. If you are not 100% sure what I'm talking about, I encourage you to just try it and see that you can still implement this in a time complexity of nmk. But in space complexity, nm. So if you really wanted to, you could even implement it in n space complexity, m space complexity, one of the two. N probably, yeah. Anyway, that's beyond the scope of this video now. So here's a way to make this problem work backwards in 2D. If this doesn't fully make sense to you, or if you think, this is very unintuitive to me, one thing you could try is to watch some of the other videos that I made about solving this problem. Maybe one of the other methods is more intuitive to you. And if so, great. Pick the one that works best for you. For me, that's not this one. If for you it is, excellent. If for you it's also not, maybe one of the other methods makes more sense to you. And with that, see you around in the next video. For now.